Okay, for this video, what we're going to look at is we're going to take those ideas we were talking about with rate laws, and we're going to look at some additional things we can do with them. Specifically, we're going to talk about what we call an integrated rate law. So what an integrated rate law does is it's an equation that's going to let us take the concentration and use the concentration to figure out the rate of our reaction. If you remember from the previous videos, we mentioned the idea that rate is going to change based on how concentrated you are. So an integrated rate law is an equation that takes that into account. So I can say something like, after 50 seconds, how much of my reactant am I going to have left? Or maybe I want to know, I want to get from 1 molar to 0.1 molar. How long is that going to take? The integrated rate law is the answer to both those questions. We're also going to talk about something called half-life. And so half-life is something that tells us the amount of time it takes to use up half of all of our reactants. This can be helpful for some things where we want to sort of get an idea quickly. Like if I know the half-life for something is 200 seconds, I know that if I want to get rid of 75% of it, I need to wait 400 seconds. That's long enough for the half-life to go twice. Because each time we have a half-life worth of time go by, we'll have a half of everything remaining, then we'll have a fourth, then we'll have an eighth, then a 16th, and it just keeps going down like that, 1/32. In most cases, I can actually figure out those problems using an integrated rate law as well, but the integrated rate law equations tend to be a little more complex and take more input, whereas my half-life will be much quicker in most cases. Or it could be that the way I've got my measurements, I might be missing something you would normally have in the integrated rate law that requires me to use a half-life. But if you know everything about the concentrations you're interested in, or you know one of the concentrations and how much time, you can use the integrated rate law as well. But when half-life applies, it's nice, it's quicker, so we tend to use those when we can. So let's talk about what these look like. So for our rate laws, I'm actually... I have my order currently listed as first, second, zero. That's fine. We'll start with a first law. So for a first order reaction. So remember, first order means that the rate is equal to K times A to the first power, which is just K times A. That's our rate. So what we're going to add is we have an integrated rate law. So this is true for any first order reaction. So for a first order reaction, the natural log of the concentration at time t, this little subscript just means at a particular time. Like if we did 50 seconds, it's what's the concentration at 50 seconds. The little subscript tells us which concentration we want because they're getting multiple in our equation. So the natural log is equal to negative rate times time plus the natural log of the starting concentration. That's A naught. So that's what it start at. What this means is if you know initial concentration and time, you can calculate what's going to be the concentration afterwards. Or you can be given two of the other pieces of information. Like I said earlier, I'm at 1 molar. That goes in A naught. I want to get to 0.1 molar. That goes in AT. Figure out the time. Also, pay attention to your units in these problems. Your rate law, or your rate constant K, is usually going to be in seconds. If your time is in minutes or hours, you need to convert that to seconds before trying to put it into this equation. The other note I want to make is I specifically want to show you how I solve for T to show you that rearrangement, as I know that dealing with natural logs, or not T, let's solve for AT. So one of the concentrations. So here the issue is that we want to get rid of this natural log. So I'm going to raise both of these to the E power. That's this whole thing here. So this is going to effectively cancel out, and we'll end up with AT equals E to the negative KT plus natural log A naught. I know that can look a little scary, but those are all just numbers that you're going to know if you're trying to solve for the concentration at time t. So K is a constant. You should know that. It'll be in the problem. T is a time. Let's say it'd been 100 seconds. A naught's the starting concentration. Let's say it was 1 molar. We plug all those things in there, and then we raise E to that power. So I know it can look a bit scary in expression form, but it's just a couple of numbers. So you can do this. And we'll look at an example with this in just a moment. So I do want to cover the rest of the parts of first order before we do an example. So the half-life is going to be equal to 0.693 over K, or you'll also see listed as natural log of 2 over K. Didn't mean to go on. So that's our half-life equation. You'll notice that for first order reactions, you don't have to put the initial concentration in the half-life. It stays the same. For other rate laws, the half-life will include the initial concentration as part of it. And then finally, and this is going to be especially helpful in lab, we want to talk about the graph that comes out of if you graph natural log of AT, I didn't give myself quite enough room, that's the natural log of the concentration, versus time. If you graph this, what you're going to get, if it's first order, and this is just for first order, is you're going to get a line that slopes down like this. And that should be straight. If I could draw a straight line, it would be straight. Where the slope is equal to negative k. That's supposed to be a k. At the edge of my tablet as well. This is how experimentally we're often going to discuss what order a reaction is. We make some measurements, and we're going to look at different graphs. So for first order, we look at natural log versus time. And we see, does it make a linear graph? And for second and zero order, there are going to be other graphs we make. So in lab, what you'll do is you can make 3 graphs, and then you can compare all of them and see which is most linear. Or with a data set in class, we might have a test question where you have 3 different graphs drawn. Here's the 0, first, and second order, and you're supposed to look at the r-squared value to tell which is most linear. As a reminder, when you're taking a trend line and you make it, one of the things you'll get is you'll get an r-squared value related to its correlation. As this is closer to 1, that means your graph is your information is more and more linear. It's a better fit. So if you need to compare multiple graphs, you compare the r-squared values and see which one is closest to 1. And that will tell you which of these should be linear. Now, let's go and look at a problem now. So this is an example of what we could ask you. So we have a chemical reaction shown at the top, and it says, I cut off some words. It's supposed to say this is a first order reaction rather than just first order reaction. So this is a first order reaction with K equal to 2.90 times 10 to the negative 4th, S to the negative 1. Note, the fact that this says S to the negative 1 actually tells you it's first order because that's the unit that's going to go with K anytime it's first order. Because since first order means rate, in this case we have K times SO2, Cl2, and it's to the first power. We know that rate is going to be in molar per second. So if SO2Cl2 is a concentration, it's going to be molar. That means that K needs to be S to the negative 1, which is 1 over S, to multiply correctly by this other factor to get molar per second. K is going to change in the different orders to have different units because you should always have a molar per second at the end with your rate. So that little aside, we've got K. And they tell us the initial concentration of SO2Cl2. And they ask, what is the concentration after 865 seconds? So we'll set up our problem. So we know it's first order, so we'll use our first order integrated rate law. The natural log of the concentration at time t, which in this case t is 865 seconds. So you could have written A865 as well, is equal to negative, I'll just write variables for right now, kt plus natural log A naught. This is supposed to be kt, and this is supposed to be a plus. Sorry about my t's and pluses look about the same. I typed test for a reason. So now let's plug in, so we're trying to find concentration for 865 seconds. That's this thing here, the AT. So before I plug numbers in, I'm going to go ahead and do what I showed you earlier. Oh, and this shouldn't have, I don't want this, I was trying to make a dash, pretend that's not there because I know it looks like a negative sign. That was not a negative, that was a dash for whatever reason. There didn't need to be a dash there. Dashes are bad, they look like negatives. So we do e to this power and e to this power, that's everything, and then these cancel. So we have AT, and now I'm going to plug in numbers as I do this now. E times negative 2.90 times 10 to the 4th, S negative 1. We're going to multiply that, so I'm going to put some parentheses around it, another set, times time, which is going to be 865 seconds. Hey, that's convenient. The seconds and the inverse seconds cancel out. And then we're going to have plus the natural log of 0.0225. Close parentheses, close parentheses. Now, I'll make a comment. When we do the setup we have here, you'll notice that Professor Phillips, we're just going to kindly not worry about the fact that the natural log has a unit there and how that works out in the end to get you molar at the end. We're just going to say it works out. You could use your rules of logarithms, split up this exponent, the e and the ln end up canceling, and you get something that has molarity in it so that it makes sense. The units do work out here, but we're going to not stress too much here with our logarithm and e exponential. We're just going to be like, hey, there's a molar there. I'm just going to believe that if I put my equation in right, that it comes out right. Having said that, make sure your concentrations are in molar before you do that, if that's what your equation expects you to have, because you can't easily just look at the units here and get them right. So we get the concentration of T is equal to, I have not done this one yet. I had to plug a bunch of things in. 2.90. I accidentally opened up my grapher. I do not need to graph a equation here. Okay. Oh, sorry. Glad I paid attention. This is a -4, not a +4. That changes the answer a lot, so you want to make sure you pay attention to that. That's up from the problem. So it's a -4, and we're multiplying that by 865, and then we're adding the natural log of 0.0225. And then I take e to that power. So what I got was everything in parentheses was equal to -4.045, and then I raised that e to that power, and I got this was 0.0175 molar. Now, a nice check on this is that the concentration went down. It is below the initial concentration, and that makes sense because it's a reactant that's getting used up. If you made a mistake and got a larger concentration, that should trigger an alarm bell in my head that goes, okay, I probably made a mistake. This is also the check I was doing to make sure I did it right. And I think if I don't have this negative over here, if I forget that, I think that's what happens here. I get way too big a number. I'm not sure, though. It does something. It'll definitely change this problem a lot if you forget that negative. So just do that check. Hey, it went down. Now, that's an example with first-order reactions. So you could solve for other things as well. Generally, this concentration is harder than, for example, time, because when you're solving for time, you plug these numbers into the natural logs, they just give you values, and then you're dividing by k. The only other thing to remember is when you're doing rearrangements, that when you have an addition, so, for example, this is not this problem, but let's take it with things. So if you have like ln x, we're going to make it look like math class, equals 2y plus ln z, that if you want to solve for y, you need to start by subtracting. Okay, I need to make sure this looks like a 2. So I can't just divide by something. I have to subtract the ln z from both sides first. And then you can divide by 2 to get y by itself. So make sure you don't just try to like divide by 2 for the whole thing. That won't help your problem here. So remember, undo your addition and subtraction parts and then do the dividing. I mentioned that because in 1211, we haven't had very many equations like this because we tended not to have variables that you were adding other variables to potentially, or other values, so you could easily just divide or multiply to solve almost all your equations. But we will have some like this where you have to do some other rearrangements. Now, let's take a look at the other reaction orders. So this is a summary of all three of them. I'm going to be giving this out on the tests that I give. So for tests you have from me, you will have access to this. I want you to be able to use this information. I'm okay if you don't memorize it perfectly, but I want you to know which things you need to apply. So if you have another professor, you might have to memorize these. So for here, we have zero order, is this equation here. And this one, I think, is very reasonable, because if you think about zero order means that the concentration doesn't change how fast the reaction goes. So it's a constant. So you take your time, at 20 seconds, however much the reaction's going to go, that's what it's going to go. It doesn't matter how concentrated it was. So we didn't have to do anything else the other part. You just take the starting amount, and you're going to subtract how much you use up, and well, that's what you've got left. There's no other business to have to deal with. That also means that the graph we're going to look for to see if something is zero order is just time versus concentration. That graph should be linear if it's zero order. And then the half-life expression, you could write it either of these ways. They're both fine. It's either initial concentration over 2K or 1 over K times initial concentration over 2. I like the first one better. If you like the second, that's fine. They give you the same answer. Now here in second order, here we're looking at 1 over concentration and how it's equal to KT plus 1 over initial concentration. So it's just a different equation. You'll do some different manipulations. You don't have to do any exponentials in this one, though. That's why I showed a first order example. Here you just have things in denominators, which I know can still bother you a little bit, but there's not as any new steps from other equations we've done before. Now, This reaction for second order is going to be looking at time versus 1 over concentration. That's the line that should be linear there. And this one will be linear in the positive direction rather than in the negative direction, like 0 in first order. And so if our reaction is second order, that's what we expect to be linear. So if you have if you've got questions we want to ask you about, like, oh, here's some data, this is what you can do with it. So for a lab, you can actually make these graphs, right? You measure the concentration, you measure the time, make 3 graphs, compare their R-squared values to see which is the most linear. That tells you what order you think it is. For a test style question is, here are 3 graphs. Look at them, and you're supposed to know, oh, that tells me the order. Also, that the slope is related to the rate constant. You're also supposed to be able to figure out that part, to figure out K from those graphs as well. So that's how you can do it in terms of things you can be asked questions about. Now, let's see. Oh, I didn't have this written here, but I do want to mention we can also ask questions with the half-life. So let's show an example of that. So let's say we're working with something where it is first order. And we're just going to make it first order A because I have to make something up to make it work. Let's say that its rate constant K is equal to 0.271 inverse seconds. I want to know, what is the half-life? Now, this question works because it's first order. If it were 0 or second order, if we go back a slide, for half-life, for 0 order, I need to know initial concentration here. Second order, I need the initial concentration here. So for 0 and second order reactions, you would also have to be given that. But for first order, you can actually leave it out because we just need to use this right here. Or this version. I'll use this version. I like it better. So our half-life is equal to 0.693 over K. And I point this out because I think this is an example of a problem where sometimes as a student, oh gosh, I don't know where 0.629 came from. 0.693 over 0.271 inverse seconds. And maybe it wouldn't be a thing for you, but for me, this is the type of problem if I saw, after everything I just did with integrated rate laws, I might go, there's no way that's what I'm supposed to do. This looks too easy. I am definitely messing something up. And no, you're not. So these problems are kind of straightforward. So what that means is that in 2.5 seconds, or 2.6 seconds, or 2.56, if you give it that long, 50% of A will be used up. That's true whether you start with 1 molar, half a molar, a tenth of a molar, 10 molar somehow. If it's a really concentrated solution, whatever it is. It's going to go down every 2.5 seconds. It uses up half. So let's consider that. So 1 molar is going to be at time 0. You'll have 0.50 molar at time equals 2.56 seconds. Then you'll have 0.25 molar at time equals 5.12 seconds. You'll then have 125 molar at time equals 7.68 seconds. Notice that each half-life, it's going to go down less and less because it is concentration depending on how fast it goes down. It's just not on the half-life. So each time you're taking a half-life, you're removing less and less of the material, which also means that this is like 50%, 25%, 12.5%. It's important to recognize that while I can say that 50% is used up at 2.56 seconds, I cannot say that 75% is not what's there at 1.28 seconds. That's not true. That's because even though half of it gets used up in 2.56 seconds, this is not linear. So what that means is in the first part of that 2.56 seconds, it's actually gone down further than 75%. I don't know the number off the top of my head, but it's gone more than that far. Because as you use up your reactants, they're going to go slower and slower. So the first half of the half-life is losing more than the second half. It's just that when you look at all of it together, it loses 50% at 2.56 seconds. So you can't make that shortcut there of, oh, it's at 75% at 1.28. Another final thing to think about is how this might be worded differently in other places. So you could have a reaction where they say, how long does it take for 75% to get used up? That's a way of saying, how do you know when 25% is left? So 75% used up is 2 half-lives. So this is one of those things where you have to think about the definition of this in the wording of the question for what you can say. It's also why I suggest reading is really good in sections like this because it helps to make sure you know what all these equations stand for. Like, what is an integrated rate law really telling me? What is a half-life telling me? What's the difference between 0, first, and second order? Knowing those things helps make these problems interpretable, because I think each question by itself is usually not too bad. Some of the natural log stuff can be a little hard, but the actual mathematics step by step isn't that strenuous in many cases. But identifying it can be, because there are just so many equations and they're different for the different orders, and you have to keep track of, like from the previous video, how do I even know what order it is? Because maybe you're not told in the problem. You're supposed to look at your data set, identify the order, and then use that to figure out what equations to use to solve later problems. Also, some of these equations, like integrated rate law, are really useful, but if you don't practice them actively, you get used to just finding rate laws, and then suddenly it's like, wait, I know there's something else I can do. I'm not sure how to do this question because it's not just find the rate law. So make sure we can identify those as well. So hopefully this helped out, and I will see you in a future video. Next, what we'll be talking about is the Arrhenius equations. We'll start dealing with the temperature dependence of the rate. So rates, all these things we're talking about, while they are temperature dependent, and we will talk about that next time.